So hello everyone, myself Mohit, and for this automated security verification assignment, I have chosen the use of ProVerif, which is a state-of-art automated cryptographic tool verifier. It is widely used in the cybersecurity industry to mathematically prove whether a protocol is secure or vulnerable to active network attackers. To address the first part of the task A, I will explain how the ProVerif encodes its inputs and security properties. So, like ProVerif encodes the input of the system or protocols using the dialect of applying the protocols using pi calculus. In practice, it means like it represents a different participations like a sender A and receiver B as a separate concurrent processes that communicates over a network channel. The actual cryptographic operations like encryptions are encoded as the abstract mathematical functions and reduction equation rather than a real code. When it comes to the encoding security property, ProVerif uses some logical queries. For example, to test the secrecy, we have wrote the expletive query for the query attacker, as you can see here, to ask the tool if attacker can ever reduce our secret variable. To test the strong authentication or the prevent replay attacks, we encode our correspondence queries which assert that if the event B happens, event A must have secretly happened first. Move to the second part of the task A, like regarding the tool's capabilities. A major strength of the ProVerif is that it automated and can analyze protocols for the unbounded numbers of parallel sessions and message sizes. This makes it incredibly powerful as finding the tricky, complex flaws like man in the middle attack or the replace attacks that can happen when multiple sessions overlap. However, a notable weakness of ProVerif stems that is from the abstraction. Because the verifying unbounded sessions is technically an undecipherable mathematical operations, ProVerif uses a over approximation. As a result, the tool can occasionally suffer from a false attacks, meaning it might fail to prove protocol secure and raise a false alarm, even if the application is perfectly safe. So now I will demonstrate how our first application, which models a basic communication protocol where a user tries to send a secret message. So this is the application one vulnerable.pv. So as you can see in the ProVerif code on my screen, we define a private private val string. So this is the string. But the vulnerability here is that severe yet simple. The data is being transmitted in the complete plain text over the public channel using the code line out. Uh, Using the code line out c variable we check if attacker can interpret this by using the property query secret val that is here. So this is the application vulnerable, and I will run it uh, using the command provif application1 vulnerable.pv. So after running that, you can see that the result not attacker secret val is false, means that it is run by the secreter. So it shows in this logic, this means false, that attacker does not get the secret. In other words, attacker successfully obtained our secret providing the application is highly vulnerable. This is to fix this. So this is the app1 fix.pv. I upgraded the application. First I added a formal encrypt function. So this is the encryption function. Uh, so this in a decrypt equation, this is the encryption function and there is a decrypt equation. What we'll do is like first I added a formal encrypt function and decrypt equation, so we securely wrap our message using a private key k. Second, I established two distinct roles, a process pa and process pb. So this is the process pa and this is the process pb, which what will do this, they represent the receiver. Now the process a properly encrypts the data. So this is the encrypting the data, and before outputting it using the pb. So furthermore, to demonstrate the true security, I will introduce the authentication events begin A and begin B. So this is the event begin A, and this is the event begin A, and B. This is the event and B. So what will happen is like this rigorously asks ProVerif if the Bob can ever accept the message if the Alice actually sent it. So like this is the like I will run it. This is the ProVerif application 1.fix.pv. So as you can see in this query is not attacked. This is a fixed version. The output clearly shows that the result not attacker is true, meaning the secrecy is full preserved. Additionally, our new authentication query also reveals is true. This proves our protocol is now successful, secured, and data is safely authenticated between A and B. So now I will demonstrate the application 2, which models a modern, more advanced man-in-the-middle and replay attack scenario. So as you can see, this is the application 2 vulnerable.pv. So what is happened inside it? This is the vulnerable version of the our second application. In this code, we attempt to encrypt our private message M, as you can see here, and using the key K. However, as we look at the keys different definition bit string, I have deliberately omitted the private tag. So like in the key, I have omitted the private tag, which shows like this simulates a deceptive vulnerability when our encryption key K is spectrally public and weak enough for attacker to know. Because of this, the encryption provides no security and there is no authentication checks in the place. So if the authentication check in the place, I will run it. It has to show that a query attacker is false. So in the terminal, I will run the command using the uh, ProVerif application vulnerability 2.py. As you can see that in the output it gives result not attacker is false. This confirms that our encryption failed to protect the data and the attacker successfully pulled the private message right out of the ciphertext. So like to fully fix this, the secure application against the man in the middle attacks, I created an upgraded version of it. As you can see here, this is the application 2 fix.pv. So first what I have done is I have ensured that the key K is now properly tagged as the private key. So this is the key key K and it is tagged privately, as you can see here. So but more importantly, I introduced as a nonce to completely prevent the replay attacks. Like as you can see in the process A, this is the nonce n new n, it is the nonce for the freshness. So I generate a fresh nonce n and include it inside the encryption block. This is the out encryption block. So when the process B receives this is the process B, and when it receive it, so it decrypts the package and verifies the nonce is perfectly intact. Just like in the previous application, I also tied this together using the explicit authentication events, so we can mathematically prove no one tampered with this message. So to verify this, I will run in on the terminal. So you can see that if it practically it should give me as the true answer. So using the command ProVerif application to fix.pv, I run this and it shows like in the output that the non-attacker is true, meaning our private message is completely shielded from the attackers. Furthermore, our authentication requirements result event end B to the event begin A is true. This proves that our proper encryption and fresh nonces has successfully secured the application against all interference. And that concludes our demonstration.